the like before Daniel like during because during lunch I checked and it worked somehow. Yeah, I know. I checked. So hello everyone. So first I want to thank the organizers. So far the conference is amazing and I enjoy the stay in Sydney very much. So today I'm going to talk about the access stabilized formalism. So as Gemma said, it's a joint work with Oliver Buerschaper and Maarten. So this is the outline of the talk. So first I will tell you the motivation, so why I think it's a nice formalism and why maybe you should learn a bit about it. And then I will spend some time on the example, which is the double semion model. So this is because our work is a formalism, so it's a bit hard to like go through all the small like properties. So and instead I think it might be nice that I just tell you about the concrete model, and I think many features of the general access stabilizer codes can be seen from this model. And after that, I will do a very quick summary of the like those small properties of the formalism. So before I really start, so I want to first tell you the definition so that you can have some you know what I'm talking about. So the Pauli S group, so on a single qubit, it's generated by alpha, which is the square root of I, and the S, which is the Clifford operator. It's a diagonal matrices of 1I, and the conjugation of S on X, it can be checked. So, and on multiple qubits, we consider tensor product of the group. So, for example, on 3 qubits, this would be an access stabilizer. And the definition of access stabilized states or codes are identical to the Pauli case. So usually you are given a group, normally by the generators. We would call a state access stabilized state if it's uniquely stabilized by all these generators. And if there's degeneracy, we would call it access stabilized codes. Okay, so let's now talk about the motivation. So since our work is a generalization of the Pauli stabilized formalism, so first I want to say a few sentences about it. So the Pauli stabilized formalism is it's quite funny because all the stabilizers are quite innocently looking like tensor product operators, and many properties of the codes or states can be obtained by just looking at commutation relation or linear algebra, and these things are not only like computationally efficient, they are like human being efficient. So in the sense that as human being, like a lot of times we can see the properties quite fast. And while it's relatively simple, the number of applications is quite huge. So for example, it's almost used everywhere when people try to study or construct like for torrent protocols, like for quantum memory or for quantum computation. And since it's a very efficient representation of quantum states, it's also used like in other applications such as measurement-based quantum computation. So the situation for access stabilizer is very similar. So first, we are still deal with stabilizers that are innocently looking tensor product operators, and we are still like checking commutation relation and using linear algebra all the times. So from this sense, it's quite easy to learn, especially for people already know about Pauli stabilized formalism. Like even the operator we add, the S operator, is just a Clifford operator people know very well. So another thing from the Pauli stabilized formalism I want to mention is the Toric code, or surface code, depends on what manifold you put it on. So I think it's interesting because, so first, it's a very practical way to actually build a quantum memory, because you can actually put the qubits on a 2-dimension like surface, and you only need to couple the qubits locally. And this is much easier for experimentalists to do, like compared to general quantum codes. And apart from that, it's a great example, like for us to understand, like some basic properties of systems with topological, orders. So because it's, for example, it's exactly solvable and simple, so we don't need to like know about conformal field theory, or we don't need to know about tensor category to understand the properties of Toric code. So in this sense, we can see the Pauli stabilizer formalism as a shortcut to like let us know a bit about the like topological models. Topological models. And while it's quite simple, the Toric code already contains feature like anyons, string operators, boundary, or twist, and all these things can be like very complicated for like general topological models, and the intuition we get from Toric code are very helpful for us to deal with like the general case. So from this perspective, the XS stabilizer, they can describe more topological model on 2D. So in this sense, it can also be viewed as a shortcut for us to understand more topological model just by using operators that we are very familiar with, like Pauli matrices and S, which are just a Clifford operation. Okay, so there's some other motivations. So for example, it's always never bad to have an efficient representations of a larger class of quantum states. Also from a computational complexity point of view, as I will tell you later, so the XS stabilizer codes, they corresponding to a class of commuting projector problems that are in MP or even in P, if there's some additional condition. Okay, so now let's look at the double semion model. So it's actually, things here are very similar to the twisted quantum double model in the morning. So the model is defined on honeycomb lattice, and on each edge there's a qubit. And an easy way to imagine the ground state is you can think the ground state as a superposition of computational bases that are closed loops, and there's a phase attached to each configuration. So here, when I say closed loops, so on the honeycomb lattice, so on each edge there's a qubit, and if it's in the state 0, we just leave it black, and if it's in the state 1, we'll draw a red line on it. And by closed loop, the red line forms like closed loops. And the phase here is in the double semion model is related to like the -1 to the number of loops here. And although in the original Levin paper, the model is defined by a commuting projector, it's not hard to see. We can actually find like stabilizers that are tensor product to describe the model. And here the ground space is characterized by these two type of stabilizers. Yeah. So let's look at the two type of stabilizers like in more detail. So the Z-type operators in the last slides is essentially the same as Toric code. So what it does is it forces the configuration into closed loops. So if you, so to see this, so this operator would force the 3 edge connected to this vertex. So either 0 qubits are in the state 1, or 2 qubits in the state 1, and this is exactly the closed loop constraint. So in the later part of the talk, I would call the closed loop subspace as a gauge invariant subspace. Okay, so now let's look at the Plaquette operator. So I would just use from now on, I would just use the color to describe the operators on that edge. So for example, the blue edge here would corresponding to X on that edge, and the red corresponding to an S. So in the XS stabilizer formalism, it's usually quite useful to look at the square of an operator. So when we do that, since it's a tensor product operator, we can do it separately, and the square of X is identity, so it becomes nothing here, and the square of S becomes Z. So So in the end, we get this set type this set operator. It's not very hard to see. This operator always have the value 1 when we restrict it into the gauge invariant subspace. This can be seen from the fact that if we draw a circle here, the gauge the closed loop condition tells us, so whenever there's there's some string goes in, it would again goes out. So the parity of the qubits here would always be even, and since the Z operator measures the parity, so you would always get 1 when you restrict yourself to the gauge invariant subspace. And this again tells us some property of the original operator. So since the original operator is a unitary, so all the eigenvalues are on the unit circle. And we know that the square of these eigenvalues are equal to 1. So the original operator, when restricted to the gauge invariant subspace, can only have plus and minus 1 eigenvalues. So next, let's try to look at the commutators. So for that, it's nice to first compute the commutator of group elements on a single qubit. So it's it's straightforward to check the group commutator of X and S are equal to I times Z. So in a graphical way, it's just whenever there's a blue edge and a red edge on the same qubit, and you compute the commutator, you would get a black edge, which is Z. So we would ignore the coefficients here in this talk. They can be computed like independently, and for the simplicity of the graph, we'll just drop them. So similarly, we can check the commutator relation between X and XS, or XS square, cube, or XS and S, and all of these gives us a Z edge. So as a simple rule, whenever there's a different color on the same edge, you would get a Z in the commutator. So now it's very straightforward to compute the commutator of 2 Plaquette stabilizers. So if we want, as on the honeycomb lattice, so we just put them like next to each other, and you can see there's 4 places where the color is different. So when you compute the commutator exactly like on these 4, the Z operator is exactly on these 4 edges. And it's not very hard to see that this operator always have value 1 inside of the gauge invariant subspace, because it's a product of 2 Z-type stabilizers. Okay, yeah. All the above observations leads to a way to build the commuting Hamiltonians, again from these stabilizers. So as I told you, the Plaquette operators, they would have plus or minus 1 eigenvalues inside of the gauge invariant subspace. So they are, when restricted to the subspace, they are Hermitian. And also the commutator is 1 inside the subspace. So they are also commuting inside of the subspace. And the subspace is, so if we just project this operator into the gauge invariant subspace, we would get the commuting Hamiltonians we want. And the gauge invariant subspace is exactly like, if we want to project it into it, you only need to project into the +1 eigenspace of Z-type operators like locally. So in the end, after you do the projection, you would still have a local Hamiltonian terms. And although, in this case, we already know the original Hamiltonian because it's just a double semion model described by Levy and Wen. But it turns out this type of procedure is actually is actually general. So for any XS stabilizer codes, we can always turn the generators into a set of commuting Hamiltonian or commuting projectors. And this kind of procedure usually, always preserves the locality if the original stabilizers have some locality. No, they're Hermitian inside the subspace. They themselves are not Hermitian anyway. So yeah, so the string operators are always something quite important in these topological models. So they would tell you some like important properties of the topological model. So for example, in the Toric code, so an immediate one thing that the string operator would immediately tells you is if you put the Toric code on a torus, you would actually have a degeneracy because the string operator don't commute with each other, and this can only happen if there's degeneracy. So here, these are the string operators for the double semion, and so for example, this is Z string, and this is a more complicated string, and the dashed line corresponding to XS3. So we can check. They commute. They commute with Plaquette stabilizers. In the gauge invariant subspace. So in this case, it's the same as Toric code. So there's two places where there's X and Z. So and each of them would gives you a -1 in the commutator, and the two of them together gives you +1 like back. So you know it commutes with a Z string. And to check this, it's a bit complicated, but as I already told you, whenever there's a different color, you would get a Z. So you can see here there's different color, and these three. So in the end, of course there's, you need to check the coefficients, and in this case it's 1, and you would obtain like two, the product of two Z stabilizers. So from this you can see that if, we are not computing the commutator of stabilizer and a string, but instead the Hamiltonian and the string would get +1 because the Hamiltonian only supports on the gauge invariant subspace where this operator have value 1. So before I go to the next part, I want to briefly say something about the quantum double twisted quantum double model. So they are already being introduced in the morning. But for our purpose, we only need to look at a very small subclass of it. So we can consider like multiple layers of honeycomb lattice, and on each edge there's still a qubit. And we still forces ourselves to those configurations that on each layers the string form closed loops. And we add a phase like to each of the configurations. Obviously, we can, this can describe, for example, 3 independent layers of Toric code or Toric code plus some double semion. But if you choose a phase like, good enough, you can actually describe some model with non-Abelian. And what we show is this type of model, they can be described by the XS stabilizer. Okay, so now let's do a quick summary of the properties of like general XS stabilizer codes. So of course, we probably want to ask whether we can compute like many properties of XS stabilizer codes efficiently. But to do that, we must first answer a more basic question. So whether give a set of generators of the group, we can always be sure that there's actually a state stabilized by them. So it turns out this in general is a question, generally is NP complete question, because we can look at this type of stabilizer. It's a tensor product of 3S, and it's a diagonal operator, so it's basically a classical constraint. And with some detailed check, you can see that this operator basically forces only one of the qubit J, qubit K, and qubit L to be in the state 1. And this is exactly classical problem called Wien3 set problem. So with multiple these constraints, you can have NP hard problem. And to see this, actually you can check this problem. This problem is in NP. You need to look at the group in more detail, and we would skip it here. But there's a subclass. Basically, if we try to ignore this kind of case, if we if we restrict ourselves to the case that the diagonal stabilizers of the group has no S in it, then we can show that this problem becomes efficient, and we can actually compute the degeneracy like efficiently, and it's always like 2 to the k. So it's very similar to Pauli case. So I mean, this kind of condition might seem a bit like arbitrary, but actually, for example, the model I told you, the double semion model, satisfies this, and all the abelian NM model we know in the twisted double model. I mean, they also satisfy this condition. So now let's look at the form of the state in a bit more detail. So I mean, we can always construct a specific basis for the code space, and depends on whether the condition on the previous slides is satisfied or not. This kind of procedure can either be like efficient or not efficient. But after that, for each of the bases, we can always efficiently find a circuit of first like Clifford gates, and then T gate is the square root of S, and the control S gate and control Z gate, which generates the state. And because of this kind of specific like structure, with some work we can show that the overlap of two bases with a Pauli operator can always be computed efficiently. So this would allow us to at least like brute force check whether excess stabilizer code have some small distance or not. So for example, if the degeneracy of the code is not very large, and then it should be very viable to check, for example, whether the code have at least distance 3 or not. Yeah, but probably in general it's very hard to check whether the code has larger distance or not. So there's also some like interesting entanglement properties of the excess stabilizer states. So what we can show is for a given excess stabilizer state psi and some bipartition, we can always efficiently find a Pauli stabilizer state VAB, which depends on the bipartition, and some unitary, such that they can map the excess stabilizer state to the Pauli stabilizer state. So this gives a like indirect way to compute the entropy for excess stabilizer states, because people know how to compute it for the Pauli stabilizer states. Also, this result tells us the entanglement properties of excess stabilizer state and the Pauli stabilizer states are very, very similar, and this reflects the fact that, for example, the Toric code and double semion model have very similar entanglement properties. So as people know, as Steve and other people's paper shows. So this is basically the talk. So here's some outlooks. So an obvious, important and probably very hard question is whether we can find some better codes. Whether we can find some better excess stabilizer codes. Yeah, and a slightly related question is, maybe we can use the way that we generalize the excess stabilizer formalism to get a more generalized stabilizer formalism, and maybe those formalism would allow us to have a more flexible way to construct codes. And also a slightly related question is, so obviously, so this type of group to commuting projector construction is, can work for other group, and so by doing that you can obtain a larger class of commuting projector problems that are still in MP. So I think it might be interesting to know what type of group would gives you like commuting projectors, and what kind of group would gives you, would make the problems like still MP, like inside MP. And last, maybe it would be interesting to understand the entanglement properties better, because so far it's very hard to tell the difference between Pauli stabilizers and excess stabilizers just from looking at the entanglement entropy. And for example, people always say like different topological order corresponding to like different like long range entanglement, and it might be interesting that if we can characterize the difference between like the entanglement entropy between excess stabilizer and Pauli stabilizer better, maybe it would allow us to understand the difference between topological models better. So yeah, thanks for listening.
Thank you very much, Xiaotong. We have some time for questions or comments.
So you mentioned that when one of these excess stabilizer state actually exists, you can find this UA and UB to map it back to a regular Pauli stabilizer state. How do these UA and UB looking like? Like, do you know what complexity do they have?
I actually forget a bit about the concrete. You probably need to do some C naught maybe, and probably X, and then just some diagonal gates, I think.
Diagonal gates in the Clifford group? Or within the Clifford group?
No, the diagonal gates can involve, like control Z, this type of thing.
Okay, thanks.
So you motivated like the Pauli stabilizer formalism and the excess stabilizer formalism by these string net models, the Toric code and the double semion. Is there any way to intuit that there's a useful stabilizer formalism from like some property of fusion category or something like this?
So you mean you first take some like fusion category and then try to construct a generalized stabilizer formalism, or?
Well, yeah. Is there some way to see that there should be an excess stabilizer formalism from some property of the string net model? Or, yeah. Would we expect similar things for other abelian, for things that have the similar structure to other abelian string net models, for example?
So I don't know whether your question is about trying to generalize the formalism or not, but yeah, I think if you, for example, if you want to look, if you want to have an excess, style stabilizer formalism on any group, maybe it's, useful to first look at the, for example, twisted quantum double model on that, defined on those groups. So, that's just my guess, so to say.
Cheers.
Well, I have a comment, which is also related to the first question, which is concerning the entanglement properties that you mentioned in the outlook. So as far as I know, your excess stabilizers formalism is like a particular case of the monomial formalism that Maarten developed. And this is related to the LME states, like locally maximally entanglable states by Barbara Krauss, which I find really neat and curious because they were developed completely independently. But I think that her motivation was to characterize multipartite entanglement. And I think that she's done a fair amount of work recently on characterizing multipartite entanglement with these LME states. So maybe by drawing this connection, you can learn something about the entanglement properties and possibly about these unitaries that Debbie was asking about.
So, maybe I can talk to you later. So there's some technical, thing. But I think it would be nice to I mean, I think this might be a nice way for the multipartite entanglement community to do something like related to the topological models. So
if there are no further comments or questions, let's thank Xiaotong again. And we reconvene at 10 past.